As you see here, now for our test object, which is the add_par library, this is the sign for the library, we generated several test cases, have full decision coverage. The MCDC coverage is not relevant because the complexity is not very high. There is no modified condition decision coverage metric possible. The coverage of design ranges is also achieved. All min-max values were tested. So we've done all of this testing. All of the needed measurement. And now when we try to also run the static analysis, it will give us an error. So when we look into the EverCheck report for what went wrong, we will see that the code generation with the embedded coder is not prepared yet. So there is a check which says that the explicit function interface needs to be defined. So before we go for the code generation, we want to prepare for the software in the loop. So basically, this is the model in the loop simulation. And software in the loop is a different kind of simulation. So in the software in the loop simulation, the source code is integrated in Simulink and executed by using the existing test cases, these test cases. The code can be manually written or generated out of the model. In our case, we will generate it out of the model. And then by comparing the cell simulation results with the expected values, and we define the expected values as reference vector, you can verify the numerical equivalence of your model and the integrated code. During a cell simulation, you can collect code coverage. As you see, we did collect the structural coverage on the model level. Let me run it again. Now the static analysis will run. We know it fails because of code generation. Now all the test cases were executed and the coverage report was provided, and we achieve 100% decision and condition coverage. That's why all of the blocks are green. And during cell simulation, you can collect code coverage for the integrated code. Remember, we are using Simulink coverage tool for collecting model and code coverage. So how do we prepare for cell? First of all, we can use the utility integrated in EverTest, which is called Integrate External C Code. With that utility, you can use the provided workflow, which supports you during integration of your C code. But first of all, the first step is to convert that subsystem, our test object, to the variant subsystem. If we run it now, we see that now we have another subsystem on top, which has this sign here. This is the variant subsystem. If we double click on that, we will see the variant subsystem with a switch in it. And as you see now, to go inside of our test object, we have a different path. So if we switch to EverTest, then we even see that this path was already adapted in EverTest. So basically, we demonstrate with that path in the settings over here that we are testing exactly that unit under test. So this is something that you can do by hand, but this way is probably a little more convenient. So the next step, we already converted the system to the variant subsystem. We don't need it to do it anymore. The next step would be to define which is our source directory. Remember, we did not generate the code yet. Let's generate the code. For that reason, we are using EverCheck. If we now run EverCheck, those are all the Simulink checks first that will be run. As we see, everything is done correctly. The state flow is not used, but the checks are still used. And at some point, we see that with the embedded coder checks explicit function interface, there is a trouble. So it needs to be defined. For those who understands how to define it for embedded coder, that's okay. You can do it by hand. In our case, we know exactly what kind of interface we need. We need to pass the parameters by value and get our results. So we just use exactly this predefined interface by using the modify button. So this sets all of the parameters that we need for the interface. So this is the interface that we now expect after code generation. If we have specific states, they need to be also listed and defined. This is okay. Now, for the traceability, we need to save the system first to run this check. It seems okay. With the traceability, I want to remind you that if we have a requirement ID over here and it is linked to some kind of a block, then if you look into the properties of it, then you will see exactly this requirement ID filter adapt 1 in the description. And this description will be also generated into the code. So you will get exactly this string in your code. All right. So this is the traceability. And then for the code generation, we will now generate the code into the production code directory C code. We already did some code generation, but I want to demonstrate how it works. So generate. And this is what we get with the embedded coder. The code is really small. We have just the RTW types file with the type defs. Without this type defs, you will not get the MISRA C compliance, so you need those. Then we have the header file in which we have two variables, which is the param variable. And this is a very cool thing that we have over here, param variable, and the limit variable. And I can go with the C code, navigate to code, boop, and then I see, okay, this is a variable here. So basically I have a bi-directional traceability. How cool is that? And then this is our code that we have over here. And so if I look for the switch, where is the code for it, then I will see that I have my comments. This is the name of the blog, so this is why it is so important to have good naming of blogs, and EverCheck supports you with that. And also we see this requirements ID over here. So now we have the traceability. We can just search for this requirement ID in the C code and we'll find it. And where is the code? Look at this. This is our code. So if in one, so the naming is used, is bigger or equal to limit, is bigger or equal to limit, then use this algorithm in one plus parameter. And the coder is so smart to understand that it needs some typecasting over here. So it does typecast on integer 8 and then returns that variable to output. And else it will take this path. It means out is equal to in one. So very simple logic, but also very clear code generation. So basically, in our case, only these 3 files will be needed, and they will be moved by our integrator, by our code generator here, to the code directory. Let's see that. This is the code directory, and you see exactly these 3 files in the code directory. So now we can imagine that all of the checks will run green. Everything is green, and we can expect that it will run exactly the same way over the API, just a little faster. You see that the complete check is about 3 seconds. After this manipulations, we can rerun our model in the loop simulation, including static analysis, then every single test, collect the structural coverage and coverage of design ranges, and we can also generate a verification report later, but we don't need it for now. So basically with meal we are ready, and we also have the infrastructure for the cell. So let's go to the next step, how we embed that C code that we generated. So we go into integrate external C code. Now we define the source directory. Sometimes there are some shared directories in the project. We do not have it right now on the unit level. Then we need to map Simulink and C interfaces. Then we generate the CIL wrapper. Then we build the max file, which is the compiled version of the integrated C code. Then we generate the CIL block and move it into this variant subsystem. Then we switch to CIL variant, and then we also can start the debugger, but we do not need it right now. This is a clear workflow how it will be done. So we can click on build. So first of all, by using the source directory and the idea of where exactly our test object is, we can do the mapping between the model in our test object. So we have inputs and outputs, and the code. So basically, we have the init function for the S function and the step function, which we need. And this is mapped correctly. And this is our C code, the way it is called in the C code. If it would not be suitable, I could also remove it and change it. But in this case, for the step function, this step parameter is correct, and so I will take it. I say OK. In the next step, the mapping tool will recognize the parameters in the model and the parameters in the C code. Here it will recognize it by name. Sometimes the names are not the same, so you will need to map it by hand. So you have this utility over here. And it also does recognize the imports and outputs. In our case, we did generate the code out of the model, so the names are exactly the same. But again, you can use the mapping utility over here if it is not the same. With the code generation with embedded coder, it's very easy. You do not need to change anything. Click on OK. And so the CIL wrapper is generated, and that CIL wrapper is very smart. It also allows you to change parameters from one test case to another. And then the max file will be built in the background. For this, we use the max setup function to install the Visual Studio. The CIL block was generated, and then we switched to that CIL block. For the switching between CIL and MIL, now we have just this button over here. You can double click on that, you go to MIL, and you double click on that, you go to CIL. So this is what was done over here. Now we are done in this utility. Okay, so I actually wanted to show you how fast it is without explanation. Let us see. EverTest, integrate C code, build. Okay, okay. Done. Close. I guess you can see that it is pretty easy to use. And now, as it is already activated, I need to just run my test case. As you see, the static analysis is not done for the C code, but we do all of the checks and we do the structural code coverage. And now if we look into the structural code coverage, we will also see the code actually for our wrapper and the code that was analyzed. Everything was covered. Let us fake what might happen if we do not cover everything. Okay, coverage of design values was not achieved. Yeah, in this case, the decision coverage was not achieved. It was not sufficient for decision coverage. And this would be the report if you do not achieve your decision coverage. So you will be navigated to exactly that line of code, and it will explain you why this piece of code is not covered. Very cool tool. We run all of the test cases, so we use the cumulative coverage all over the test cases. It will be gathered together, and here we achieve 100% coverage. So now we've done our CIL test.